This video assumes two things. One, that you've seen part one in the oxidation state videos, and two, that you are familiar with Lewis dot structures and bonding. If you're not, you're probably not going to get a lot out of this video. The first situation I'm going to cover is for a polyatomic ion that involves the same atoms. In other words, something like peroxide, where we have two oxygens bonded together, and there's also an overall charge of -2. And I'll quickly contrast that with just a neutral oxygen molecule. Note that an oxygen atom naturally has 6 valence electrons around it. If you're watching this video, you should hopefully be comfortable at this point with the idea that an O2 molecule looks like this, where we have a double bond between the oxygens and each oxygen has 2 lone pairs. Well, we've already seen a situation where both atoms were the same, and the fact that there's now a double bond between the atoms changes nothing. We would say that there is still an equal pulling of each electron, and so we say each oxygen takes 2 electrons, and so ultimately each oxygen has 6 electrons to itself, and the oxidation state would equal 0, since this is the natural amount of electrons. Now for peroxide, we have this. O is single bonded to another O, and each oxygen has 3 lone pairs around it. So since we still have the same atom, we would still say that there is an equal pulling of each electron, but we would also say that each oxygen takes 1 electron, since there's only a single bond here, and ultimately each oxygen would have 7 electrons, the 6 from the lone pairs and the 1 that it's taking from this bond. But since oxygen naturally only has 6 valence electrons, it's like we're pretending that each atom has its own extra electron. Thus the oxidation state is -1. So hopefully that all makes sense. Now I'm going to do a couple more examples. I'll start with carbon monoxide, where the carbon atom has 4 valence electrons and oxygen atom has 6 valence electrons. So the carbon monoxide molecule looks like this. Carbon is triple bonded to oxygen, and each atom has its own lone pair. Oxygen is more electronegative than carbon, and so let's analyze what the oxidation states of each atom would be, starting with carbon. If carbon were to lose all of these bonding electrons, then it would only have these 2 electrons over here left. So it would thus have a +2 oxidation state, since it naturally should have 4 valence electrons. On the other hand, if we're going to pretend like oxygen is going to take all 6 of these bonding electrons, then we're pretending like it has 8 electrons total, taking this lone pair into account. Its oxidation state is -2, since oxygen should naturally have 6. Notice that the states add up to 0 in agreement with CO being a neutral molecule. But let's look at this polyatomic ion over here. Once again, each carbon should have 4 valence electrons naturally, and each oxygen should have 6. Carbonate structure looks like this. Carbon is surrounded in a triangle by each oxygen. 2 of them have a single bond, and 1 has a double bond. Now you may have learned about resonance hybrids, but we don't need to understand that theory or acknowledge it to do this problem and figure out the oxidation states for every atom. In fact, it would make things more complicated to deal with. Once again, oxygen is more electronegative than carbon. So let's start by quickly looking at these 2 single-bonded oxygens. If each oxygen were to take both of the electrons in those single bonds, then the total electron count is equal to 8. We would say its oxidation state is thus -2, since oxygen naturally should have 6 electrons. Now this oxygen, we're going to pretend like it takes all 4 of those electrons in the double bond, and thus it also would have a total electron count of 8. Thus its oxidation state is -2. And as for the carbon, well, we're pretending like it's lost all of those bonding electrons and has none of its own left. And so it has a +4 oxidation state, since it should have 4 electrons, but we're pretending like it's lost them all. Notice that the states add up to a total of -2 in agreement with the overall charge of the species. So that's carbonate for you. Again, no convoluted set of rules necessary, just an understanding of the oxidation state definition.